hit record. All right, so let's get started. So it's a pleasure for me to be able to welcome Professor Anthony Pullen today. Anthony is a professor at New York University and also a visiting scholar at the Center for Computational Astrophysics. Anthony graduated from Southern University and then got his PhD at Caltech, which is where I first met him. After that, he did postdoctoral positions at JPL and at Carnegie Mellon, and then joined the faculty at NYU in 2016. So Anthony's work focuses on really understanding the large-scale structure of the universe. He's worked on a variety of aspects of that, including galaxy surveys, cosmic microwave background work, and I think most recently has been focused a lot on using line intensity mapping. And he is going to tell us all about that today. So over to you, Anthony.
First off, I want to thank Andrew for hosting me for this visit. I really apologize that I could not be there in person. I was really excited to come visit California, to visit Pasadena. It's been a long time since I've spent a significant amount of time there, so it's really sad that I couldn't arrive. But I hope to sometime in the future I'll get to visit in person. But today I'm excited to talk about my work, which today I'll be discussing how to probe galaxy physics with line intensity mapping. This is a set of projects where we want to say if we have observations from both line intensity mapping surveys, which I'll discuss further, as well as galaxy surveys, how can we use that information in order to learn something about the galaxies that make up our cosmos? So I'm very excited to talk about this today. It's a pretty unsolved problem, and there's a lot of opportunities for learning about the physics of our universe. So I just want to acknowledge institutions that are collaborating with me. That includes the Goddard Space Flight Center, as well as the Simon Center for Computational Astrophysics in New York City, as well as Carnegie Observatory, specifically collaborating with my former grad student, Sheng-Xu Yang. So here's an outline of my talk. So first, I will give an introduction to line intensity mapping and what we hope to learn from it. And then I'll discuss line intensity mapping simulations, which will be, and as well as a galaxy inference model, which we're trying to build from the simulations, which will be used to be able to connect observations to properties of galaxies, which we hope to be able to measure. After this, I will also talk about the EXCLAIM survey, for which I'm the science lead. And it's a survey that's going to launch that is scheduled to have its launch next fall of 2023, and we're going to discuss what we plan to learn from that survey. And finally, if I have time, I'll discuss some cosmology applications from line intensity mapping that my group has been working on. So first, so let's just start with the cosmic dawn. So I'll know. After the cosmic microwave background was formed, basically all the universe was consisted of hydrogen and helium. In this period, there were no stars, so this is known as the star age. Just then 400 million years after the Big Bang, the first matter was able to collapse enough in order to start star formation as well as galaxy formation. And this is when you had the first galaxies and stars. And after that time, those stars emit UV radiation, which reionize the intergalactic medium of the universe. And then as that evolution of time passed, you were then able to have galaxies be able to group together from gravity to form galaxy clusters, and all this formed into the large scale structure we see today. And so if we were able to directly observe these galaxies and the intergalactic medium, we'd be able to learn a lot about the physics of the cosmos to learn more about our universe. However, one problem is that we're actually in our galaxy surveys, we actually miss a lot of galaxies. So this is a simulation of a galaxy survey from the Very Large Array, where the red dots represent the galaxies that could be observed by this telescope, then the black dots represent all the galaxies that are too faint to appear in a galaxy survey. you see there's way more galaxies that are too faint. These gray dots representing those galaxies are way more numerous than the red dots of what we can actually measure. And so the question is, how can we statistically probe all the galaxies, not just the ones that show up in our bright galaxy surveys? One way this could possibly happen is if you look at this simulation here of microwave emission constituting from all these galaxies. And the key thing is that if we were able to measure all this microwave emission directly, we'd be able to see the fluctuations in large scale structure that are sourced by not just the brightest galaxies, but all the galaxies in large scale structure. And so the question is, can we probe this directly? So line intensity mapping is one way to do this. So in particular, what it does is it measures the aggregate intensity from large 2D pixels in multi-frequency bins. So what that means is that you can have, it's in the same way that you have cosmic microwave background maps, which tabulate the intensity of the sky in 2D pixels. You can also replace the cosmic microwave background with intensity from large scale structure, from galaxies in large scale structure. And then as those galaxies redshift along, in those galaxies redshift, they will emit in different frequency, that have different signatures in frequency. And so you can use that information in order to figure out the distance of each galaxy, of where the emission is coming from the line of sight. So the key thing here, though, is that you're not imaging individual galaxies, because that's very expensive to do. That's what galaxy surveys do. They take it's a significant amount of time for each galaxy in order to measure its position on the sky. The key thing is that you're measuring the aggregate intensity from all the galaxies. And so you can still sample large scale structure without measuring the position of each individual galaxy. And so this allows, and this is great, but one thing that's great about this is that it's much faster to scan across the sky for this, to do this type of measurement than to do a traditional galaxy survey. So the picture on the right, this is a simulation of what line intensity mapping data could look like, where on the sky you see fluctuations due to large scale structure. So this is a sort of a transverse map for one individual frequency bin, whereas if you put each of these maps and stack them in frequency space, you see the fluctuations in large scale structure due to perturbations along the line of sight of large scale structure. And with line intensity mapping, you can, again, because it's much cheaper to do a line intensity mapping survey per area than a galaxy survey, you can map much larger volumes with the line intensity mapping survey than you can in a traditional galaxy survey. You can also map structure much earlier in time, because because the key thing is that you can measure structure from much fainter objects, and with those objects potentially being much higher redshifts. And so this is great for early universe physics and gravitational physics, because you can probe very large scales. We're mapping very large volumes, meaning you can probe structure on very large scales. In addition, being able to map emission at much higher redshifts, which means you can probe structure earlier in the universe. So this is great for cosmology. At the same time, you can also get you can also map intensity as a function of frequency on the sky. And so you actually map many lines can actually contribute to the line intensity maps that we form. And so this is great for probing galaxy evolution, because each of those spectral lines can be sourced by various properties of galaxies in large scale structure. And so this is what I'll talk about a lot today, is how we use line intensity mapping to probe galaxy evolution. So the way this works is that because we're not imaging individual galaxies, any measurement you attempt to do with line intensity mapping will be a statistical measurement. And so we have to talk about the statistics of large scale structure that you can measure with line intensity mapping. So the most well-known one is the power spectrum. So power spectra have been used in cosmology measurements for for over 30 years. The idea being is that you can, with the power spectrum, describing how different perturbations of intensity can be correlated across length scales. Okay, and so this is a signature of large scale structure, which can vary depending on your model of large scale structure formation. Okay, what determines the power spectrum? Well, it's the number, density, and luminosity of galaxies, because while power spectra are measured in galaxy surveys based on the number of galaxies in each pixel, for an line intensity mapping, you're measuring the intensity in each pixel. And that intensity is going to be sourced by the number density of galaxies. So if you have more galaxies per volume, you're going to get a higher intensity. In addition, if you have brighter galaxies, you're going to get a higher intensity. And so the one drawback for the power spectrum is it's only sensitive to the mean and the variance of intensity perturbations. Okay, so and that's just the way it's structured. So you can use the power spectrum in order to measure the line intensity as well as the matter distribution, because both of those contribute to both of those influence what the level of power you're going to see in your large scale structure map is. Okay, one thing in addition you can do is you can cross correlate two maps with each other in order to and then the great thing about that is that you can be immune to you can remove effects from both noise bias, where two maps will have noise, but those noises won't be correlated, which will allow you to measure the signal that you want. And also foregrounds can be removed this way as well, because if you have two maps with foregrounds that are not correlated, then that could be eliminated when you correlate two maps together. And so, however, as I mentioned earlier, the power spectrum is only sensitive to the mean and variance of intensity perturbation. So other statistics are also being developed in order to really sample the full amount of information that is present in line intensity maps. One example of this is a probability distribution function of it's sort of a probability distribution function. Specifically, one statistic that has been constructed is known as a voxel intensity distribution. And this is basically a histogram of intensity fluctuations on a map. And the key thing is that it's actually samples sort of non-Gaussian structure that wouldn't get picked up in a power spectrum map, in a power spectrum measurement. And in particular, can probe the full distribution of intensity perturbations. So if you see on the right-hand side, sort of this top here is an example of what a power spectrum looks like, where large scale fluctuations live over here and small scale structures lives over here. Whereas this picture is what a voxel intensity distribution looks like, where you see this tail of the intensity distributions here, and intensity fluctuations here in this distribution, and that's caused by a non-Gaussian structure that wouldn't be picked up if you were just to measure a power spectrum. And in particular, we're going to see later on that using both of these statistics together actually gives you more information than what you would get separately. So we're going to discuss that later.
I think there may be a question from Dan.
Yes.
Hi, I'm really excited by that part. I'm interested in this. So I guess I have a question here. Do you do the voxel intensity distribution then at a fixed scale, or is there somehow an average distribution here over a range of scales or a mix of scales?
Right. So this has been developed over, usually you'd use a fixed scale, like you have a fixed pixel size that you use based on your instrument. So typically you'd want to it's limited by your beam size for your instrument, as well as the spectral resolution. One thing one amount of formalism that hasn't been developed that is that my group is that we want to actually start working on is how to formalize that. So all this has been formalized for power spectra forever. So we also have to do this for and it's actually much more much more complicated to do it for this than what was done for the power spectrum. So, but that's something that
Okay.
we're
Yeah, I mean, I'm excited to talk about this obviously a little bit more offline, given a paper Andrew and I did a couple of years ago. But this will be fun. Thank you for clarifying that. That's really interesting. I'm excited.
What is T1 and T2 in that diagram?
So T1 and T2 represent two different intensity maps, where T is your brightness temperature, which is a unit of intensity.
Two maps.
So in this case, so I wasn't actually on this paper. One of my postdocs was on this paper when he led this paper, and what he did was he used this is the map for CO, the CO carbon monoxide line from the J equals 2 to J equals 1 transition. And these were the same maps, but assumed that they were coming from different detectors such that their noises wouldn't be correlated. Yeah.
Thank you. Now it's clear.
Any other questions? Okay, great. So I just wanted to highlight 3 measurements that have been done. There are line intensity mapping measurements that have been done previously. So of course, I'll highlight Shang-Chi Yang's measurement, which she did while she was in my group at NYU, where we constructed a limit on the C2 intensity. That's this purple line here, where the y-axis is intensity, and the x, and then over plotted on here are some models of ionized carbon emission, which vary depending on the minimum halo mass that you assume for star formation. Excuse me. But also I want to highlight some other measurements that have been done, specifically a cross-correlation measurement of BOSS quasars with Lyman alpha emission from the BOSS that were extracted from the BOSS maps. BOSS being one of the surveys for the Sloan Digital Sky Survey. And so here is their limit of basically a cross power spectrum, for a correlation function. And then here is highlighted a measurement of CO emission and used in order to construct limits on the density of molecular hydrogen, which is a line that you can't, which has emission that's it's pretty much impossible to detect because molecular hydrogen doesn't have a permanent dipole, but it's highly correlated with CO. And so if you measure CO, then you get a good handle on you could potentially get a good handle on the amount of molecular hydrogen in the cosmos, which is a precursor to star formation. So one thing I would like to then, so all that's to say is that as we develop the machine around this, we want to be able to use line intensity mapping in order to learn about both the cosmology as well as to learn about how galaxies form and how they evolve over time. So in order to do this, you have to think about the inputs, the models, and the outputs. So one thing that we have is that we start off with line intensity maps. We use those line intensity maps to develop statistics. But at the same time, you need some model, just like any other time that we try to do a measurement, and particularly in large scale structure, you need some model that predicts both, if you have some model for galaxy evolution, and how that connects to emissions, as well as how cosmology connects to clustering of galaxies. Then you can use that information together to make a model for these statistics that you already have data for. And then if you have statistics data, statistics model, input that into some kind of solver like a Monte Carlo Markov chain, then you can measure properties. Then the ideal is that you can measure properties of galaxy. You can measure galaxy evolution phenomena as well as cosmology. And so to see the sort of state of play, we have, first part of this is the data side. So for the data, there's much innovation, what are the best statistics to use in order to get the information you want. And so there's much innovative work on that, but we do have statistics. I mean, we have We know how to calculate a power spectrum. We know how to now calculate. We're almost there on how to calculate voxel intensity distributions. And so with that information, we should, and much more is still being done on that, but we're pretty far away. And at least, you know, we have what we need. More statistics would be better, but we have the initial tools that we need in order to do measurements. Even if we just had the power spectrum alone, we could still get a lot of information from that. The other thing we have is cosmology clustering models. We know generally how matter clusters, as far as you know, so we know that that's that'll work to first order. There's still some questions about how galaxies cluster, but we can do a pretty good job by just you know, having a clustering bias that as an extra parameter that you have to fit for. That's pretty good for the sensitivities that we have, particularly for line intensity mapping. One day that's not going to be good enough, and we're going to have more sophisticated models. But for now, we have enough what we need. What we're really lacking though is a model for connecting galaxy evolution to emission model to emission. This is something that much more work is needed to be done in order to even know how to have some ideas for how galaxies could evolve. We have lots of simulations that work on this, but lots of them disagree on what they generally predict, and it's not always clear necessarily how galaxy evolution then turns into emission signatures that you can then use for observations. And so this is why I'm focused on this part in particular, is because it's pretty underdeveloped, and if we don't get this part right, it could really mess up everything as far as trying to understand galaxies from data. So and it could also bleed into cosmology as well if you have degeneracies in these models that could affect measurements of clustering. So this is something that we strive to figure it out. So I think everyone here probably knows what a dark matter halo is. I don't think I have to do a big review on that. But just to be clear, because we know that the way our models are set up is that we relies on the idea that galaxy emission is source. Galaxy emission is what sources the line intensity maps. Obviously, there is emission from the intergalactic medium, but for many of the lines that we're considering right now, like carbon monoxide emission as well as carbon emissions, these are mostly sourced by galaxies themselves, and with these galaxies clustering in dark matter halos. Since the dark matter halos trace large-scale structure, that means that the emissions from the galaxies should also trace large-scale structure. With the and you can also model halo luminosities with the dark matter not emitting directly, but the galaxies that are clustered around that live in the dark matter halos, those galaxies summed together will produce a luminosity for the dark matter halos. And so this halo luminosity is often what's modeled in the literature. So when people try to make models of intensity mapping in large scale structure, typically what they model is a luminosity, is a relation of relating a halo luminosity to the mass of that halo. The idea being that larger halos will tend to have more galaxies, and bigger galaxies, which will tend to have more material, and so when they emit, they'll be brighter, and so you generally have a connection between dark matter halo mass and luminosity. So many of these models that are currently in the literature are what we call empirical models, and these are models where you extrapolate from correlation seen in data or simulation. So you either have data which you will be given all the galaxies as well as what the emission is, and then you can try to use that to make an empirical model, or you will have an actual simulation that predicts both where the galaxies are and the luminosity, and you try to build a model from there. Okay, and this is really what's used in the literature. It's reason why we use it is it's very inferable. If you have a simple analytic model, you can use it you can input it in an inference model very easily. However, there are drawbacks to this approach, serious drawbacks. Well, one, these models are typically extrapolated from outside of the range of observations. So you can, and one example of this is this plot on the right, where I plot the CO, the halo luminosity for CO emission as a function of halo mass. And these are different, these curves represent different models in the literature. And one thing you see here is that the most of the models seem to agree around this mass, around 10 to the 12, whereas they tend to disagree at both higher masses and lower masses. And the reason why that is because most of the galaxies that people observe in bright galaxy surveys come from halos that are around this mass. And so that's what you're gonna, and so their models are all going to be set to fit at that observation, but you're not going to get very different, based on different assumptions, you can get very different predictions for halo mass ranges that haven't been constrained. Also, too, there are other issues where because for spectra, you typically have multiple lines that you would want to be able to map. But one problem is that you have multi-line scatter, where not each line is independent, of course, because multiple lines can be sourced by the same galactic processes, and those, but empirical models typically don't capture that information. They typically allow every line to be independent, or if there is some correlation, it's very crude. And so you're not going to get all the information if you have wrong assumptions about what the luminosity scatter is. And then also too, if you have multiple lines, you want self-consistent predictions where, and the problem is if you have an empirical model, you can't be sure that, as opposed to a more physical model, you can't be sure that, if you have an increase in one line and an increase in another line, and that's actually, that those increases are actually make sense, given the physics of the actual galaxies. So one way around this is to have you try to use hydrodynamic simulations. Hydrodynamic simulations are better because they actually implement the physics directly, and they're not, and so you can trust them. So you can trust them more to capture a large dynamical range of conditions than you can with an empirical model. However, there are some limitations. Hydrodynamic models still lack the resolution to simulate things on processes in interstellar medium on subparsec scales. So, and these could be the sizes of actual molecular clouds within galaxies, and so that's going to require. And so you still many of these simulations still have subgroup modeling that's implemented in the simulations. Also, too, these simulations are very expensive to perform. Some simulations take a year to come up with a new simulation, and so that it can be very. So if you want to get a full sampling of what type of maps could exist in the large scale structure given some initial conditions, that could be that you can typically have a limited set of galaxies. There are tools, there are methods that smart people use in order, like zoom in simulations, in order to try to circumvent some of these issues, but you still have limitations. And then finally, one issue, and then finally, sort of the most jarring issue is that these processes in simulations are difficult to interpret, and because they're very complex. You're talking about individual you're talking about macro particles of gas that are used in order to allow them to interact, in order to form stars, in order to form galaxies. And then the issue is that those processes are very complex to then turn into a simpler model that could then be used to have inference. You have to, and so using a hydrodynamic simulation directly is just difficult to use. You can make some headway with possibly by using emulators, but then that involves machine learning, which can have its own complexities as well when trying to calibrate those models. So what we've been using as an alternative approach is what is known as semi-analytic modeling. So I'm sure you guys probably heard a lot about semi-analytic modeling because Andrew Benson has Galacticus, which is a semi-analytic model for galaxy clustering. And so what we use is semi-analytic models in our work in order to basically in order to simulate galaxy evolution and emission by basically applying star formation and galaxy evolution models onto dark matter halos. What that means is that we have dark matter halos from an in-body simulation, and then we have physical models that describe how, given a mass, how many galaxies should form, how much gas should be in those galaxies of different species, whether it's H2, H1, ionized hydrogen, neutral hydrogen, molecular hydrogen in different species, and then what stars should form in those regions, particularly depending on how much molecular hydrogen in those regions, and then determining the metallicities of those stars in order to be able to see the metallicities of galaxies. So these semi-analytic models are constructed such that you do have model. They're not empirical models in that you just say, well, if you have a halo of a certain mass, you get this much emission. They're actually dependent on the individual galaxies that exist within the halos and how they evolve. But at the same time, you do still have actual relations that determine these processes, and these relations being calibrated from data in simulations. Okay, this calibration can work this way, where you have, for example, here's a plot where you have C2 ionized carbon luminosity as a function of star formation rate, and basically the models are set up such that you fit these data points here measured by the ALMO survey of luminosity versus star formation rate in galaxies. And then whereas the full distribution would live in these gray dots here, these gray pixels here, where these are all the galaxies that are predicted to be present in the semi-analytic model. And so this is the information that we use. And so the key thing is that on one hand, you're still using information that you didn't have to extrapolate from, but now we have more physical models, and so that allows us to predict what the emission should be. It should allow us to predict for multiple lines because you're actually predicting the physics, and so as those physics it's the physics of the galaxies that then used to predict the emissions. Actual correlations between different lines should be present because they're being sourced by the same physics. Okay, so this is sort of how this works in practice, where you start off with dark matter halos, you then predict the galaxies that exist in those halos, you predict the gas that's present in those galaxies, and then you have from there you can then model the emission that's expected from that gas. So here's some work that we've done in the past. So here is Shang-Chi's work that she did when she was a grad student, both here where she made simulations of line intensity maps using semi-analytic models. So here she simulated ionized carbon, and as well as the cosmic infrared background. And then in addition to that, we then used the SAM to then construct the empirical models of C2, CO emission, as well as CO1 emission. One thing that my group is working on now is how much information we gain from running the semi-analytic model fully in a simulation versus just assuming this empirical model is the case. And so what we're going to use that is to find out basically the amount of information you would lose by just using an empirical model, as well as what questions in galaxy evolution would be necessary to use the full simulation versus just semi-analytic model versus just using an empirical model calibrated off that semi-analytic model. So then building these models, the next question we want to answer is about inference, about how can we use these models in order to learn about galaxy evolution. And the truth is it is a very challenging topic. For one, so I mentioned earlier a measurement that was done with using CO emission in order to constrain the amount of H2 density in the universe. However, and in that measurement, they used a constant what's known as a parameter alpha CO, which relates the CEO luminosity to the amount of H2 mass that will be present in a halo. And so this is a number that has been measured from data typically, from different galaxy measurements in the local universe. And so and then extrapolated to higher redshifts. But what we find is that you actually, in our semi-analytic model, we actually find we actually find that you can't treat this number as just one number for all redshifts, nor can you treat it as independent of halo mass. And so what we find is that basically, when you have different assumptions about what this parameter is, you will get very different measurements for H2. And so this is a problem. We won't want to be able to produce a measurement where, based on just individual model, we get vastly different measurements for physics. And so we actually, right now, one thing that we're working on is how to build better models that actually take into account the uncertainty in the modeling, but can actually allow for, and then another problem with this is that this assumes that this number is independent, to where the mass of H2 only depends on the luminosity of CO, but it actually turns out that the LCO could vary with other parameters, like the amount of, like the metallicity, or the, like the metallicity or amount of stars. And so one thing you'd want to do is be able to implement a luminosity model that takes into account several galaxy properties, and then uses that information in order to be able to have a more robust measurement of properties. And so this is something that my group has been working on very aggressively. Specifically, what we started off is modeling what we call a conditional galaxy property distribution. And what this is just a distribution of, if you're given a sample of galaxies, if you want to say, okay, what's the average star formation rate for those galaxies? What's the average metallicity for those galaxies? What's the average H2 mass for those galaxies? And different properties. What we want to be able to say is to actually be able to measure a distribution of all these properties, because these properties are going to then tell you something about the physics of how galaxies evolve. And so, and the key thing is that if we were to know this information, this would be very ideal for both galaxy surveys and line intensity mapping surveys. For example, for line intensity mapping surveys, this halo luminosity, halo mass relation can be directly related to this distribution. Specifically, if for all the galaxies, you had a distribution of properties, and then if you knew for a list of properties, galaxy properties, what the luminosity of those galaxies would be, you can then convolve these two, or you can then convolve these two distributions together in order to then be able to predict what the luminosity mass relation. And this is the thing that could actually be directly measured from line intensity mapping surveys. And so this is what we and so the key thing is that we want to be able to construct models of this distribution, construct models of this, what we call a line luminosity relation that relates galaxy properties to luminosity, to spectra, and then use that information to be able to then backtrack an observation to be able to measure this distribution. So we assume, so in our semi-analytic model, basically there are 5 parameters that govern what the what all the properties of a galaxy are, and those 5 parameters are the H2, the H2 mass of that galaxy, the star formation rate, the stellar mass, the size of the galaxy, of the galactic disk, as well as the metallicity of that galaxy. So these 5 major properties actually govern in our semi-analytic model, govern all the properties of the galaxies. And so, and then one thing that we can show is that given line luminosity relation, a relation between galaxy properties and luminosity, you can actually basically pretty much all the observables that people measure in the literature in galaxy evolution can be written in terms of these two functions. So, for example, a luminosity function can be written in terms of this luminosity relation as well as the distribution of objects, because luminosity function is just the number density of galaxies that emit in a specific range of luminosities. And so we can also use this to, we can also construct observables like intensity, the voxel intensity distribution, fundamental planes can also be written in terms of these 2 functions. there's a lot of information there that I don't have time to get into, but that's but basically pretty much all the observables that people typically want to measure can be written in terms of these two functions. So one thing we want to do first, though, is to be able to measure this in simulations to get an idea of what this distribution could look like. So here is a triangle plot where we show, given these 5 parameters, what the distribution of the what this galaxy property distribution will look like. One thing, and here is a plot in a specific mass range specifically for galaxies associated with halos with masses between with log masses between 11.4 and 11.6. And however, we in the project we're finishing up right now, we actually measured this distribution for a full redshift range of same predictions between z equals 0 to 10, and then a halo mass range of a halo log mass range of 10 to 13. So 1 million halos were simulated in order to do this, and 1 million halos were tracked at each redshift in order to simulate this distribution. And one thing the most interesting thing we found was that this distribution can be accurately modeled using what's known as a Gaussian mixture model, which is the sum of 2 multivariate Gaussian distributions. And so what we find is that a Gaussian mixture model, or one component models for the Gaussian mixture model actually does really well. So just one Gaussian actually is pretty good. Using 2 Gaussian mixture models actually can, and the way we say it's good is to look at this plot here, where we can predict observables, and we see that the Gaussian mixture models actually does a good job of predicting it, where you see here that if you assume just one component, you can get predictions that are on order of 10% of of the actual SAM, for the full SAM. Whereas if you assume 2 components for a Gaussian mixture model, you can get precisions within less than a few percent. And so, so this is for the star formation rate density. This on the right is for basically a star formation rate function, or distribution of star formation rates. And here is here's a correlation between two quantities. So this is star formation rate here, and the stellar mass here. And as we see, you get a distribution. So the color represents the actual SAM, whereas these orange lines represent the predictions from the single Gaussian component Gaussian mixture model. And so as you see is that it actually does pretty well. This is important because if we want to actually do inference with this, we're not going to be able to use the full SAM. We need some kind of parameterizable model in order to then do a measurement. And so it's a good sign that a Gaussian mixture model actually does a pretty good job, because that will reduce drastically the number of parameters we'd have to measure in order to do inference. And so that's a good sign. And this is work that was done by my former grad student, Yu-Cheng Zhang, who's now a postdoc. One thing, of course, is that this was based just on the semi-analytic model. If we actually look at, we actually repeat this for illustrious TNG, and we get different results, which is a good thing, because that means that different models will actually predict different distributions, which we can then, and the goal is to then make a prior that sort of accounts for the, how far the parameters in the Gaussian mixture model could vary, and then the goal is that a data set from both line intensity mapping data as well as galaxy survey data could then be used to constrain the parameters for the Gaussian mixture model, such that you can actually learn something. Then you can measure directly the galaxy property distribution to learn something about the galaxies, including the faint ones that don't appear in galaxy surveys but would influence large scale structure. So that's so most of that was discussing the galaxy property distribution. One part of that is crucial is to predict this line luminosity relation that relates galaxy properties to spectra. So a postdoc who's working with me, Patrick Bracey, has been working on this part. And one thing he's been able to do is we've been able to construct use Gaussian processes to construct a model for this relation that actually is accurate to that actually has a precision of smaller than 1%, or being able to predict, given the properties of a galaxy, to be able to predict the amount of the luminosity in CO and C2. So this is very exciting work that to be able to, and then the goal is that if this can be treated with this much precision, it'll be very helpful to then do an inference measurement where you try to relate observables to galaxy properties. But the next step being is to actually try to implement this in simulations and data in order to see how well this measurement could actually work in practice. So next I want to talk about survey I'm part of, the EXCLAIM Line Intensity Mapping Survey. So EXCLAIM stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. This is one of a few pathfinders for line intensity mapping that will be launching, that is sort of in this window where so that will be taking the sort of the first steps of true line intensity mapping data. So the line intensity mapping measurements I mentioned earlier, we're using I mostly use broadband photometry, where you have large frequency bands that are used to measure intensity. But in order to use line intensity mapping full power, you need some resolution along the line of sight. And so being able to have instruments with very high spectral resolution would be key to doing line intensity mapping. And so that's EXCLAIM is one of these surveys that will serve that function. So EXCLAIM is a collaboration with over 40 members, spanning 8 institutions. And some questions that we want to answer is we want to be able to track star formation, particularly around redshift 2 to 3, where star formation begins to, at later times, begins to decrease, even though clustering it continues increasing. We want to be able to measure the abundance and excitation of the molecular gas that forms stars. We want to measure properties of gas in the Milky Way galaxy, which is also something that EXCLAIM is going to be able to measure. And then finally, this survey is going to serve as a sort of a pathfinder for future surveys, which will have more sensitivity in order to be able to do cosmological measurements. So we're going to use, this survey is going to use cross correlations in its extragalactic survey. So if here's a map of the sky, the survey of the Milky Way is going to cover here. It's going to cover 90 square degrees, whereas the extragalactic survey is here and is going to cover about 320 square degrees. In order to be sure that we minimize any photon contamination, we're going to cross correlate our maps with quasars in galaxies from the Sloan-Digital Sky Survey, to be able to measure power spectra and voxel intensity distributions. So it's scheduled to have its first engineering flight in fall of next year. If that's successful, we will then, and that flight will include 1 spectrometer. In the following year, we'd expect to have our first science flight, which will include all 6 spectrometers. Here's a paper that I just recently posted on archive a few weeks ago, where we predict what power spectra are expected to be measured from EXCLAIM, as well as the voxel intensity distribution, which I'll show in the next slide. But here we find that we do forecasts to show how sensitive EXCLAIM would be given its sensitivity. And so here are predictions for what the power spectra should look like with both cross intensity autocorrelations as well as autocorrelations as well as cross correlations. And one thing we measure here is we construct this parameter A, which is just an amplitude in order to see how well we can detect the power spectrum, or when averaging over all scales. And one thing we find is that using this, we have a very high chance of being able to detect both C2 and CO emission from large scale structure with using EXCLAIM. Specifically, we should have a sensitivity in order to be able to discriminate between different models of CO and C2 emission. as you can see from these plots, with each of these dots representing different, well, in the C2 map, each of these dots represent different models as calculated at different redshifts, while the CO plot shows different models for different line transitions of CO, so that we'll be able to measure. And then with signal to noise is between 4 and 11, depending on the true model of emission. So here with C2, we have enough sense. So CO is lower sensitivity. We have lower sensitivity to CO than C2, just because CO is a less bright, is a fainter line than C2. So we will still be able to detect the power spectrum, but we won't be able to detect much more than that for CO. For C2, we should be able to detect. We should have a sensitivity to be able to learn some science. For one, we should be able to also measure the voxel intensity distribution. We should be able to use this information from both the power spectrum and the voxel intensity distribution to then measure the intensity of C2, depending on which model is the correct model. But this is assuming a more optimistic model from Hamza and Padmanabhan in 2019. And this is the model based on the SAMs that we've calibrated. There will be a more pessimistic model. And so depending on which model is accurate, we'd be able to make a detection. But either way, whether we have a detection or not, we should be able to discriminate between different models of C2. Also, if you want to parameterize a luminosity halo mass relation, we should be able to detect that. These are some mock measurements based on the fiducial model of what we'd be able to detect for different parameters in that model. And then one thing that's cool is that that's great, is that we should be able to if the more optimistic model is true, we could actually make a measurement of the star formation rate density, specifically at redshift 2.7. We should be able to measure this. This plot shows the orange bar is what EXCLAIM will be able to measure, and the gray crosses represent the other basically star formation rate density measurements from the literature using direct imaging. And the key thing here is that these measurements are competitive with those direct imaging measurements. And more importantly, this would be a global measurement, whereas the direct imaging measurements have to use specific bright galaxies that show up in the field in order to make the measurement. This comes from all the emission. This comes as a measurement from all the emission, including from the fainter galaxies. And so this should be in that case, then it should be a measurement accounting for all the galaxies in the cosmos. So in order to do this type of measurement, you have to be able to connect C2 emission to the star formation rate. This assumes that we're using a simple empirical model to relate, specifically a power law, in order to relate luminosity to star formation rate with alpha determined from simulations. However, as we discussed earlier, there are more robust methods of doing this. And so this is what we use for this forecast. But one thing we will explore in the future is using something like using like a SAM coupled with a model that includes a galaxy property distribution to possibly get something more robust for this type of measurement. And so that's something we'll be exploring in the future. So I think I'm pretty much out of time. So I think I'll just end here, where I'll just discuss the plans for the future, where one thing we want to do is, we're going to construct is, we're going to use the semi-analytic model in order to construct more empirical models, and then see for other lines like the 21 centimeter line and the H alpha optical line, in order to see are those in order to be able to see, can we use simulations, basically what do we get from simulations versus using empirical models. And then we're also considering how to could we use models where we directly connect line intensity mapping to other properties like star formation, like the star formation rate. And so this is something that my group is working on now currently as well. Again, as I mentioned earlier, we want to be able to build more realistic statistics models of faster simulations. So my group is also working on this as well. In the future, as the data comes from EXCLAIM, we expect to be able to perform that EXCLAIM analysis. We're going to perform that EXCLAIM analysis. So I'm the lead of the team that's going to be working on that. And so we're going to, and then one thing we possibly will consider is cross correlations with other galaxy surveys like DESI, as the data set is populated. And then finally, as I mentioned before, we want to be able to test our conditional galaxy property distribution method with data as well to see basically get a test run of how to do this type of measurement, as well as to use simulations to sort of model what we can expect future TC mapping surveys to do, because we expect that future TC mapping surveys will be a lot more sensitive. They'll be for galaxy evolution as well as cosmology, and we want to be able to do the best job to prepare for when those data sets arrive. So these are just my summary. This is just my summary of in the sense that we want to be able to do line intensity mapping science. We're right now building the methods that are that are going to allow us to do that robustly. More data is coming in, and so it's much opportunity to be able to explore this space. Thank you for your time, and I'll be happy to answer any questions.
Great, thank you, Anthony. We do have time for questions, and I see Dan already had his hand raised, so go ahead, Dan.
Hi, that was great. Thank you. I got excited a little bit earlier. So on one of your last slides, you showed that you have to assume the C2 goes with the star formation rate to some exponent of alpha. And you'd indicated that you kind of need the simulations to guide you into what alpha might be. And I was wondering whether there was anything in the data that allowed the data to tell you what alpha would be. You know, if you had to marginalize over it, or if you had to just, you know, is there just something in the data that would help you with it?
Right. So yes, that's correct. So one way so if you have galaxy survey data of local galaxies, you could use that as a way to guide it, and while marginalizing over alpha. That's something we actually assumed when we made these forecasts that alpha would have some uncertainty.
Right.
And so we actually did marginalize over prior when constructing these forecasts to account for that. So you could, yeah. So actually in the forecast, so we actually used two methods to try to forecast limits on the star formation rate density. One was to use intensity map. One was to use intensity mapping data as a previous paper from another person who used the measurement that Cheng-Chi Yang and I did, was able to use that data in order to make an estimate for alpha. And so we considered a model where we used that information, and then as well we used a different model where we had alpha from using the semi-analytic model, and that had some. And so for that, and then we allowed like a 10% uncertainty on that, just to be clear. But so the key thing is that you certainly could use alpha from it's whether you use it from the simulations or data, you can use that. One thing that so this is a part of the stage where you would need if you had bright galaxy surveys to inform this choice, then you could have some uncertainty on it, and then allow the data from line intensity mapping to you marginalize over that parameter in order to have robust errors, systematic errors for this type of measurement, and that's something that you can do.
Yeah.
So that's something that we would do in our measurement.
Thank you.
Steve, you had a question?
I have two questions. The first is, I just don't have a very clear picture of what the radio spectrum looks like. In the optical, there would be a problem where you'd have to resolve an ambiguity between what line you were looking at and what redshift you were looking at, like 3727 at low redshift and Lyman alpha at high redshift. So is it the case in the radio for these lines that they're just much stronger than anything within several octaves of any other lines where you don't have that ambiguity, or how do you deal with that problem?
Right. So, well, two things. So one, CO and C2 are some of the for some millimeter spectra. C2 and C2 well, CO and C2 are the brightest lines in that regime, and so that's helpful in order to in the sense that other lines would contribute less. But the key thing also as well is that we're cross correlating these lines with either galaxy surveys or with other lines, such that anything that's not coming from the same redshift should cancel out when doing a cross correlation. Because you're looking at, if you think about large scale structure, if you take two parts of large scale structure that are at different redshifts, then there will be a different regions of large scale structure. And those two regions themselves shouldn't, if you try to cross correlate those two regions together, those two regions shouldn't correlate with each other in large scale structure. Those two regions, if you try to cross correlate them together, they should cancel out. And so that's sort of the key. That's sort of the key mechanism where we can try to get emission from specific redshifts. Yeah. Does that answer your question?
Yes, it did. Thank you. The other question has to do, it's also sort of comes from my experience in the optical, where there are two approaches for doing sort of generalized high redshift surveys and things, one of which is to identify the individual sources, which you spoke about a little bit at the beginning, and the other is to average the intensity over large areas. And it actually is the case that in the optical, where the sort of natural resolution is an arc-second typically, it's more favorable just in terms of signal to noise to identify the sources. And there's a few faint sources that you'll miss, but you'll actually get almost everything. So the question is, what changes in the radio that makes it more favorable to actually average over a big area? One possibility is it has to do with the resolution, where you just, you don't have, the instrument doesn't have the angular resolution that you actually get in the optical. But then the other thing is in the wavelength direction, you actually have a lot of resolution typically, like in some of the maps you showed. And again, you can pick out individual sources either on the sky or in wavelength or both. And so I wonder about the actual balance between making a survey and basing statistics on individual sources versus averaging over big areas or volumes.
Right. So it really depends on the specific line. So this is a question, it's a very important question, like specifically the question of what's an optimal measurement to do for a galaxy survey with bright counts versus a line intensity mapping survey. I think you're specifically talking about an average, like an average over a whole sky, which is a little bit different, but I think it's sort of the same question, similar type of question. And so it really depends on where those galaxies are coming from. So if you have a distribution where most of the galaxies are coming from higher mass halos, then you can be in a situation where you're not going to get much more information from faint galaxies, and so then a galaxy measurement would be optimal. Versus if most of the galaxies are faint, but still in a regime where they're bright enough to where they would reasonably contribute to the intensity map, then getting the emission from those faint galaxies could be very beneficial. And so this is something that you could actually measure with simulations to try to see how much information. It's something that we think about often, like, based on the minimum mass that produces star formation, what does that mean as far as the emission? You see, you could have situations where, okay, what we definitely see is that, going from 10 to the 12 solar mass halos to 10 to the 11th, 10th does significantly, 10 to the 10, 10 to the 11 does significantly affect the observables that we see. And so those galaxies do still play a role. But then, you get situations where going even farther down doesn't actually add much to the intensity model. So because then at a certain point, the galaxies are so faint that they're not contributing appreciably to the intensities in pixels. So it's something that it's model dependent that you have to analyze for each specific problem. But you get a general idea depending on which line you're discussing.
Thank you.
Let's see, Anna, you had a question?
Yes, thanks. So I actually have a follow-up on what you were just saying, Anthony, about what is the contribution to the line intensity mapping as a function of stellar mass? And this is kind of motivated by the broader question of how close the hydrodynamic simulations are to be kind of able to forecast any of the line density mapping signals.
Right. So yeah, so stellar mass is definitely what we found, particularly when we construct these luminosity, these line luminosity relations, is that the line luminosities are sensitive to, for like CO and T2 are sensitive to stellar mass. Not as much as star formation rate and metallicity. We do find that both star formation rate and metallicities significantly contribute to the line luminosities, whereas stellar mass also has a role to play, but it's not as sensitive to stellar mass as it is for star formation rate and metallicity. But it still contributes, and you can imagine that if you try to do a measurement of the distribution of properties, that you would get some information on the stellar masses of galaxies. And as far as how it goes down, so I do not have a prediction though for so one thing we do have though is that it definitely so for halo masses, but about 10 to the 10 is far enough to where you get basically all the information. How that translates into, so I don't have, I mean, if you have an efficiency of a guess about what,
Probably
about
less,
10%, right? Then that will be your estimate for, so I guess 10 to the 9 stellar mass would be sort of the limit. I would say, like the stellar mass in a whole halo, not the stellar mass within an individual galaxy, but yeah.
Right. Okay, thanks.
All right, I don't see any more questions. So let's thank Anthony again for a really interesting talk, and thanks everyone for joining us.
Thank you.
Awesome. Thanks, Anthony. I'll see you in a couple of hours, I guess.
Right.
Yep. See you in the afternoon.
That was
Bye.
good. Bye.